Hello, Roz. This is part 2 of our course review. We are going to do questions 6 through 11. That's the plan. That's going to cover functions and exponential relations and functions and applications of exponentials. It'll bring us right up to trig ratios, right before trig ratios. Okay, so the first question, question number 6, has g of x written as a transformation of f of x, and we want to list the transformations on g. First thing we want to do is make sure that this is in a factored form, because this is not shifted left 3 or right 3. We go g of x equals -2 times f of, I'm going to remove a factor of -1/3. This is a situation where it's easy to accidentally think, oh, 1/3 of 3 is 1, and you put a 1 there. It's also easy to catch it with distribution, though. 1/3 times 1 won't give you 3. 1/3 times 9 will give you 3. You're doing 3 divided by 1/3. How many thirds are in 3 wholes? There's 9 thirds in 3 wholes. Check with distribution to catch that. Transformations, when written in this order, are best read from left to right. You have a vertical reflection, or a reflection across the x-axis, a vertical stretch by a factor of 2, or your y values are being doubled. That's from the x-axis again. You have a horizontal reflection. That's in the y-axis. You have a horizontal stretch, watch the reversal here, by 3. You are dividing this argument before you run it through the f input. That means that your inputs can now be 3 times larger what they used to be. Same reversal happens horizontally here. You have a horizontal shift. Right 9. You are subtracting 9 from your inputs before you do the rest of these operations on them. That means that your inputs can now be 9 larger than what they used to be. And a vertical shift, up 1. Cut. In part B, we are asked to write a specific equation if f of x is the square root of x. Well, this should be pretty straightforward. I'm going to use the factored form that I have. I think it'll help me with domain and range on the next question. G of x is going to be, I'll read from left to right, -2 times f of. What does f of mean now? We're defining that f of means the square root of. The argument for the f machine is no longer just x, though. It is now -1/3 of x minus 9. So that becomes my radicand, or the thing that I'm taking the square root of. The addition of 1 should be clearly placed outside of the square root of. Big set of square brackets there might help clarify that. Okay. Asked to state the domain and range of G. We could do this algebraically, but I think most students found the most success when they use sketches. And it took us a while to accept that strategy, but the sketches are very, very useful here. So I'm going to take that approach. I'm going to draw an original radical. It would have a vertex at 0, 0. It's vertical out of that origin. It goes up and to the right. Its domain is x is greater than or equal to 0. Its range is y is greater than or equal to 0. And now I'm going to perform these transformations. I am going to perform a vertical reflection. That changes my range. Vertical stretch doesn't change my domain or range. Horizontal reflection, that changes my domain. Horizontal stretch, that doesn't change my domain or range. Shift right 9, up 1. Usually spend time to draw a good copy. I kind of feel like this diagram isn't that messy. If I label that G and I label this 9, 1, I think I'm ready to use my sketch as my justification for my domain and range. I'm going to say that the domain of the relationship G, that's what I was asked for, right? Yeah, is the set of all x values that are less than or equal to 9. X is going to be any real number. That satisfies that. The range on G is going to be the set of all y values, or G of x values, such that y is less than or equal to 1. Y is an element of the real numbers. See, I could reason through that here and say if my radicand needs to be positive, then this needs to be negative, and if x minus 9 needs to be negative, or neutral, sorry, then x needs to be less than or equal to 9. And you could solve that as a linear inequality if you like. But the sketch is going to be useful for part D, very useful for part D anyways. So why not do that? In part D, we are asked to find an equation for G inverse of X. And I am going to start with my sketch here. Inverting is an exchange of domain and range. I exchange inputs and outputs. The ordered pair 9, 1 is on G. That means the ordered pair 1, 9 is going to be on G inverse. I can kind of fudge the rest of this if you like, because I'm never good at visualizing it as being reflected across line. Y equals X. I might be able to handle it here. Let's see. The down is a negative vertical direction that inverts to a negative horizontal direction. So this curve should open left. Left is a negative horizontal direction. That's going to invert to a negative vertical direction. So this curve should open down and to the left. But notice that G only has one arm. So G inverse will only have one arm. I need to check my equation when I get to the end of this question and make sure that G only has one arm. I'm almost ready to write the equation here. It would be up to me to make sure that I invert the stretches as well. It's probably best to show your work algebraically. I believe those are the directions on some of our quizzes and tests. So for D, what I'm going to do is I'm going to replace the G of X with the traditional Y. I'll keep this in a factored form, and when I rearrange, I'll try to keep it in a factored form as well. My rearrangement might look a little bit different than we would normally rearrange a linear relationship, but that's because my goal is to keep the function in a factored form. I'm going to communicate that I am inverting. I could say here comes the relationship for G inverse, is when X changes into Y and Y changes into X, that needs to be communicated because it does not follow mathematically. Like if this line is true, this line is false. So you have to say I am inverting here. Okay, I suggested a long time ago that we try maybe undoing some of these operations on one step. So I'm going to try that with you now here. Here's the order of operations that I'm going to undo. I'm going to undo the addition, then I'm going to undo the multiplication, then I'll undo the square root of, then I'll undo the multiplication by negative 1/3, then I'll undo the negative 9. Let's just see if we can handle this without writing out another line, because that's what 1, 2, 3, 4, 5 operations, and maybe I don't want to write 5 lines. Maybe if I had just gotten to it instead of talking about it, I would have been done by now already. But anyways, so I'm going to subtract 1 from both sides and just give myself a little bit of space here. Okay. The next thing I'm going to do is divide both sides by negative 2. Just kidding. No, I'm not. I'm going to multiply by negative 1/2 so that I see that in a factored form. If I divide it by negative 2, it's not wrong, but I want to see it in a factored form. The next thing I'm going to do, so I would be like this right now, is square both sides. I square the entire right-hand side. I have to square the entire left-hand side. Okay. That means that I am squaring the negative 1/2 as well. The negative 2, that was a vertical reflection and vertical stretch. That becomes a horizontal reflection and horizontal stretch. It has to be inside the brackets for that to happen. Okay, where are we now? I would have the square root of. Instead of dividing both sides by negative 1/3, I'm going to multiply both sides by negative 3. That'll undo a division by negative 1/3, or sorry, a multiplication by negative 1/3. And then, shoot, didn't leave enough space. Let me erase that because I'm using pencil. I add 9 to both sides. And that'll give me actually the y value isolated. Now you feel free to take more steps than this. Check your work carefully. But if you have mastered rearranging, you can usually visualize this happening like that. You also have your sketch to help you out and the language of inverting to help you out. So notice we're expecting a vertex at 1, 9. There you go. The vertical reflection inverts to a horizontal reflection. The horizontal reflection inverts to a vertical reflection. The vertical stretch by 2 inverts to a horizontal stretch by 2, reciprocated. A horizontal stretch by 3 inverts to a vertical stretch by 3. This is what I mean by sometimes students can just translate from one equation to another by inverting the transformations. We have one problem, one very common problem left over, and that is this equation right here is a quadratic that has 2 arms. It has a vertex of 1, 9, and it goes left and right. The domain and range of G are naturally restricted. You can't put in a value greater than 9. You will never get a value out greater than 1. But in here, it looks like you're allowed to put in X values that are greater than 1, and your sketch shows you that you're not. So the best place, I think, to put this is in your conclusion. When you say that G prime of X is, it looks like a quadratic. It's half of a quadratic, I suppose. So it follows this quadratic curve, except it has to be restricted so that X is less than or equal to 1. You're cutting off one of the arms. Use your sketch to see that, because I don't think any students saw that algebraically in this course. Okay. Question 7 is an opportunity for a little bit of communication. It says, explain the difference between the inverse of a function and the reciprocal of a function. This is pretty wide open here. Not entirely clear how much I need to explain, but I'll try to give a couple of different explanations. Let's say, given y equals f of x, the inverse, which is going to be written, so I'm going to introduce the notation to demonstrate that I understand the difference in the notation. F inverse, I think saying a mapping statement is probably one of the best ways of visualizing this. Maps x comma y to y comma x. Maybe I should define it. Inverting, exchanges, domain and range. We were not asked specifically to mention what happens graphically. You could mention that when you invert a relationship, it's a reflection across line y equals x. The problem with that approach is that if you ask me to explain graphically what happens to the reciprocal of a function, there's a lot of different things that could happen. So I find it difficult to generalize. Let's introduce the reciprocal, which I'm going to use another function letter and call it g of x. I think we usually used r of x, but I want to mix things up just once. Oops. Which is f of x to the exponent -1, or the reciprocal of f of x. And I'm going out of my way here to use, sorry, there you go. Not much better. To use the symbol -1 to show you the difference between the inverse symbol and the reciprocal symbol. We now have more experience with this. We can compare, say, theta equals the inverse sign of y over r to the cosecant of theta is the sine of theta to the exponent -1. This is not an exponent, and this one is. This is an inverse, this one is not an inverse. That's why I don't like putting the exponents, writing like sine squared of theta. What does the reciprocal do? Well, let's start with a mapping statement. That's a pretty straightforward way of demonstrating my understanding. It maps xy to x comma the reciprocal of y, as long as y isn't 0. So if you wanted me to explain what's happening, I suppose I would say that reciprocating, it's still an exchange, isn't it? It's an exchange of the numerator and denominator of outputs. Reciprocating exchanges, numerators and denominators of outputs. I've already mentioned the restriction there, so. Okay. When asked for an inverse or a reciprocal on some sort of final evaluation, sometimes students just pick the wrong one. You want to make sure that you're clear on the difference. You'll be doing inverting and reciprocating in advanced functions. Okay, question 8, some exponential work. We are asked to simplify by hand or evaluate by hand. Make sure you know how this works. We know our calculators are useful tools, and some calculators will be able to just spit out, most calculators will be able to just spit out the correct answer here, but I am interested in seeing that you know how this works. Negative exponents cause a reciprocation of your base. 4/3 there. Fractional exponents tell you which root you are taking. like that. You can use the property that the power of a quotient is the quotient of powers. So I'm going to take the cubed root of my numerator and denominator. The cubed root of 27/8 is going to be 3/2. Keep those brackets around your base so that it's clear that your base isn't just 3. And then the fourth power of 3/2 is going to be 81/16. And there you go. I don't know what 27 to the exponent 4 is. I don't want to make my numbers larger before they get smaller. That was 8a, sorry. 8b, we have 6 times the square root of 200 plus 3 times the square root of 8. 6 root 200s plus 3 root 8s, those are not, you could imagine that they're not like terms. They're not counting the same kind of thing. This is not going to be 9 square root of 208. Let's simplify these radicals and see if we can get them counting the same type of thing. I'll show all of my steps here. In 200, I see a factor of 100, which is interesting because it's the largest perfect square factor in 200. In 8, I see a factor of 4, which is a perfect square. Technically, there is a factor of the square root of 100 in the square root of 200. There's not really the number 200 in this expression. Then I'll use another power law that says that the power of a product is equal to the product of powers. So this is 6 times root 100 times root 2 plus 3 times the square root of 4 times root 2. This is not distribution. These powers exponents do not distribute across sums and differences. So this would be 6 times 10 times the square root of 2 plus 3 times 2 times the square root of 2. 6 times 10 can simplify to 60. 3 times 2 can simplify to 6. And in this case, I mean, it's not luck. The question was designed so that we could simplify down to the same radicand. You now have 60 root 2's plus 6 root 2's. You read it in English, and it should make sense. Okay, instead of trying to memorize that I add the numbers out front and keep the numbers underneath kind of thing. This is like 60 apples plus 6 apples. Or, I don't know, this is 6 degrees Fahrenheit plus 3 degrees Celsius. You need to convert them so that they're counting the same units. Okay. Question 9 is a skill we haven't used a ton of since our work in exponentials, but it does come up a bit in advanced functions and calculus. We're asked to rationalize the denominator and simplify. 2 examples. Example A is a monomial type. Example B is a binomial type. 2 different approaches. It is only the root 2 that bugs me here. Of having a factor of 3 in the denominator isn't a problem. I want to rationalize root 2. I can't square the top and the bottom. I need to multiply by 1. So I'm going to multiply by root 2 root 2ths. That will give me 8 times the square root of, well, the square root of 5 times the square root of 2 is the square root of 5 times 2, which is the square root of 10. I'll do that a little bit faster. 3 times root 2 is going to be 3 times the square root of 2 times the square root of 2. That's the square root of 4. Maybe I could have done that one a little bit faster as well. Because I multiplied by root 2 by design, so that root 2 times root 2 rationalizes to 2. I'm not in a rush to go to 6, though, because I like my numbers getting smaller before they get larger. I see a factor of 8 in the numerator and a factor of 2 in the denominator. Let's divide both the numerator and denominator by those factors, and we will end up with the simplified expression for root 10 divided by 3. Root 10 has a factor of root 2 and root 5. Neither one of those are perfect square factors, so we know we're done. Example B, we had some more experience with conjugates when we were working with identities, but it wasn't really rationalizing. Actually, there was one identity where multiplying by the conjugate was the best approach. So I'd like to get rid of the square root of 3 in the denominator, but if I multiply the denominator by the square root of 3, that's going to show up as a factor in the 6 here, because I have to use the distributive property. So to make things tidy up, I could remove a common factor of 2 first, and my numbers would be a little bit smaller. It's not that advantageous here, but if you want to try that, let me know if you think it's much easier. No, I'll multiply by 1 in the format of the radical conjugate of the denominator. Let's get some brackets around everything here. And I'm going to show my work. I think my advice often centered around maybe focusing on the denominator first, so that you're not doing 2 different types of operations on the same line. Let's see. I'm going to multiply these two terms by those two terms. So the 6 times 6 will give me 36. I'll have a plus 24 root 3. I'll have a minus 24 root 3. Now, some students skip this step because, again, by design, they want this to simplify to 0. But that's not going to happen in the numerator, and sometimes students just think you're doing this times this and this times this, and they forget about the middle terms. So I think it's a better idea to always show it. A negative times a positive is a negative. 4 times 4 is 16. Root 3 times root 3 is going to be root 3 times 3, also known as root 9. Still have some work to do in the denominator, so let me focus on that. I'll have 36 plus 0 of those root 3's, so no more irrational parts there. Minus 16 times, well, the square root of 9 is 3. Still more work to do in the denominator. 36 minus 48. I'll have a negative factor in the denominator, which I'll want to take care of. Excuse me. Take care of eventually. Now's a good time to do some work in the numerator. Should I expand the numerator? Probably, because I'm hoping to find maybe a factor of 12 or 6 or 2 or 4 or 3 in the numerator, but I don't see one. Also, I can see that root 3 times root 3 will also rationalize. If this was just a monomial, if this was just 6 right here, then no, I would not want to distribute because then I'm ready to factor. So you can't memorize that I should always expand or I should always factor. You need to look at your specific situation and determine what is the best choice. Kind of like identities. 2 root 3 times 6, 12 root 3. 2 root 3 times 4 root 3. Let's write that as 8 root 9. Negative 5 times 6, that's minus 30. Negative 5 times positive 4 root 3, that's negative 20 root 3. Let's see here. I think I can collect these on this step. 12 root 3 minus 20 root 3, that's negative 8 root 3's. I'm not in a rush to evaluate the rest. I've got a couple of other spaces here. Maybe I can do, well, no, not in a rush. Root 9 is 3 minus 30. 8 times 3, negative 8 root 3 plus. Okay, this one, yeah, I might try to go one step faster here. I see 24 minus 30. Let's just go to minus 6. So that on this step, I can remove a factor in the numerator. I see a factor in the numerator of negative 2, leaving me with a quotient of 4 root 3 plus 3. And then I'm set up with a numerator in factored form and a denominator in factored form. Let's simplify this expression and remove the negative factor in the denominator while we're at it, and write this as 4 root 3 plus 3 divided by 6. Now, this expression looks like it should simplify a little bit more, but if you look at your numerator, you can see your numerator can't be factored anymore. What students often want to do is write it as 4 root 3 sixths plus 3 sixths, so that they can reduce 4 sixths down to 2/3 and 3 sixths down to 1/2. But I'm going to argue this isn't much simpler than that. You have two separate terms instead of one quotient. It also took a couple of steps to do, but both are acceptable. This is fine to end in. Okay. Solving exponential equations was a bit of a hurdle for us because we learned how to solve linear equations. Some students learned how to solve quadratic equations. Other students just kind of memorized an algorithm or a formula. Hopefully you learned a little bit more about what it meant to solve a quadratic equation and point out that we ended up solving linear equations. Well, solving exponential equations is a little bit different. Not really trying to isolate x right now, and there's not some quadratic or exponential formula you can just substitute into. It requires a little bit more maybe a little bit of trial and error and a bit of a different approach. Our argument was to solve this equation, we try to write both sides as a single power of a common base. We're in decent shape right now because both sides are written as single powers. They're not written as a common base. I'm looking for a common base between 81 and 27. 9 is a popular choice. Well, it's not that popular. It's a common thought because 9 is a common factor of both of these, but writing 27 as a power of 9 is not really that easy. I know you could handle it because you would take the square root and then cube, so it's like the 3/2 power of 9. You'll probably find it easier to use a smaller base like 3.
So I'm going to write both of these as powers of 3. 81 is 3 to the exponent 4. I might be using a bit of trial and error there. 1/27th is 3 to the exponent negative 3. Be careful here. I'm not ready to set 4x equal to negative 3x minus 1 because both sides are not written as a single power of the same base. This is still a power of 3 to the exponent 4. Use your exponent laws. You have x groups of 4 groups of 3. That is 4 times x groups of 3. To simplify the power of a power, you keep your base and multiply your exponents, in other words. But I don't want to just memorize something. This means that if my powers are equal and my bases are equal, that my exponents must be equal. I think I might distribute on that step as well. I add 3x to both sides. Now I'm looking at a linear equation, so I shift gears. I'm going to try to isolate x. I do that by undoing operations with inverse operations to maintain equilibrium. And there's my solution. Okay. Question 11 is our last one for today. It is modeling functions as a function of time, t in years. The first one says a population of 30,000 grows by 7% every 3 years. So I've got a rate of 7% or 0.07. That means that my base I want to use is going to be 1 plus 0.07. I need my base to represent the 100% that I keep plus the 7% that I increase. Sorry, a little bit of review here. Usually we can use models P of t equals P0, 1 plus or minus your growth rate or your base to the exponent t divided by h, the length of a growth or a decay period. Okay. So by having a base of 1.07, that's how I grow by 7%. I don't see a need to use any sort of vertical shift here, like with the temperature of the coffee cup question. So I believe that 30,000 will be my initial value, and I can use that as my vertical stretch to just change my original dependent intercept of 1 to a new dependent intercept of 30,000, base of 1.07. Now if I put the exponent t up here, that's going to grow by 7% every year. I want it to wait until 3 years have passed before it has a growth period, so I divide my exponent by 3. Graphically, you can visualize this as you take your function that used to have a y-intercept of 1, you stretch it vertically by 30,000, so that now it has a y-intercept of 30,000. And then with a base of 1.07, you would be at 1.07. You'd be 7% higher after 1 year. You want to stretch that horizontally by 3. Here's a k value of 1/3. Stretch that horizontally by 3 so that it happens after 3 years. The other thing you can do, and this worked really well with our multiple choice quizzes, is just try a number out. P of, I don't know, 12. P of 12, you should have grown 4 times because there's 4 groups of 3 years in 12 years. If I substitute in 12 and I divide by 3, I get an exponent of 4. Part B says 30,000. Sorry. $30,000 car depreciates in value by 7% every 6 months. All right, so my rate here is a decrease of 7%. That means that my base is going to be 1 minus 0.07 or 0.93. If my car is depreciating in value by 7%, it's 7% off, then I'm only going to be left with 93% of my original value. Let's say v of t. Was I asked to declare my variables? It'd be good practice. I'll do that in a sec. Original value of $30,000. Base of 0.93. And then this says it depreciates in value by 7% every 6 months. I can't say let n represent the number of 6 months because the question told me to use t as the time in years. My length of a decay period here is 6 months, but that needs to be measured in years. If I did t divided by 6, that would mean that it decays by 7% every 6 years. 6 months is 1/2 of a year. If I do t divided by 1/2, that should be simplified to 2t.
Let's just try that out by substituting in a number. If we wait for 3 years and the card depreciates every, bad example. If we wait for 4 years and the card depreciates every 6 months, then in 4 years, it should have depreciated 8 times. V of 4 is going to be to the exponent 2 times 4, or 8. Looks good. You'll deal with more exponential relationships in advanced functions. In calculus, you'll learn that you can actually use one common base for every single growth and decay period and just use your k value to affect how quickly it changes. You may have seen that in maybe like a chemistry course. Okay. Keep going, and I'll see you next time for our last lesson and the last section of review.